Hello and welcome back. Today we're going to talk about arc length, and it'll be, I think, an interesting discussion about how arc length actually relates to bicycles. So this background actually came from a presentation I did for an engineering class in high school. So we were talking about the elements of the design changes of bicycles from the very early or the first bicycle. So I think you'll find it interesting. So first we need to actually talk about circumference. So circumference is the distance around a circle. It's the perimeter of a circle, in other words. So we want to find out what is the length of this black line. Well, if you imagine trying to measure the length of the black line, if you had a tape measure or a ruler, as you measure it, you'd have to roll the ruler around the circle, which would be really difficult and be hard to make sure that it didn't slip or anything like that. So just as a different frame of reference, another way that we can find the length of the circumference is to actually roll the circle out, or to roll the wheel if that's what we're dealing with in this case. So what we can do is we can take the circle or the wheel and we can mark where it starts, which would be the point tangent to some flat surface here. And then we can roll the wheel one full rotation until it marks up, or it matches up with that point that goes all the way around and reaches this point right here, letting us know from a reference point that it's made one full rotation. Then all we have to do is measure the distance from the starting point to the ending point, and measure that flat distance along the ground. So it's a lot easier to measure this distance along the ground of one full rotation than it is to actually measure the round surface of the wheel in the first place. All right, so the way that we can calculate the circumference would be by our formulas. Now, there are two formulas we can use. So 2 pi r is the most common one. It's kind of the default that we go to, which is 2 times pi times the radius. In this case, our radius would be 6 inches. It's a 6-inch radius circle. So when we plug in 6 for the radius, we get 2 times the radius, which is 12 pi. So that tells us that the distance that this would travel would be 12 pi inches. Now, notice this is exact. So 12 pi, because we're not multiplying by some irrational number pi, meaning that it repeats, it's a decimal that repeats indefinitely, also cannot be written as a fraction. So it's an irrational number. So if we leave it as 12 pi, that's exactly how the distance and all of its precision. But we might want to have more of an approximation. So the way we can find that approximation would be to plug it in our calculator. So I guess you might have just saw it there, but if we do 12 and hit the pi button, which is right above our caret key, which we also enjoy, and hit enter, it's going to leave it in reduced form, which is 12 pi. So hit the convert button, the one right above enter, and that'll give us a decimal approximation about 37.7. So this is going to be a distance of about 37.7 inches. Now notice I'm using the approximately equal to, the wavy lines, right, instead of the equal to sign, because it's equal to exactly 12 pi, but it's approximately equal to, as a decimal approximation, 37.7 inches. Now the other formula you might have is if we are given the diameter, which is 12, it's just 2 times the radius, then you can just write 12 pi, right? So it's pi times d, or pi d is also another way we can find the circumference. So the circumference would be 12 pi that way as well. Either way, it doesn't really matter. Another way that you might have seen this actually in action is with a measuring wheel. So in golf courses or anywhere that they would need to mark out a distance, like shot put, if you're doing some field games or something like that, they can find the distance by walking with this measuring wheel. Now, as long as the measuring wheel stays on the surface and doesn't skip, and it sticks to the surface, then you're fine. Otherwise, it'll tell you haven't gone as far as you actually have. So you have some error there. So on this one, the measuring wheel, let's say that the measuring wheel, it doesn't matter what circumference it has, but just to make our math easier, let's say that this one has a circumference of 1 meter. And so the circumference is 1 meter. We want to find out what would the radius of this wheel be if it had a circumference of 1 meter. So just plugging into our formula, circumference is 1 meter. We want to solve for the radius, the green mark here. And then so the distance that it travels in one full rotation is 1 meter. All right, so we want to divide by 2 pi. So whenever we do that, we're going to have 1 divided by 2 pi. Okay, and we can put it in our calculator just like that. It's going to give us Okay, so that actually did half of pi, so there's a problem there. You might actually just use the, I'm glad that happened though, you might just use the n over d button. That way you can make sure that you put the parts in the denominator that need to both be in the denominator. So 1 divided by 2 pi. That's probably how I would put it in, because if I didn't know better, I might have gone with that for my answer. So the actual answer is going to be 0.159 meters, and that's going to be our radius. So if we convert that to centimeters, we're just going to, because there are 100 centimeters in 1 meter, so we just take that and multiply it by 100. That's what the centi part means. So it's going to be 15.9 centimeters for our for the radius. So if we want to make our own measuring wheel, we would just need to make a wheel, construct it. You could do one out of cardboard or something like that, with a radius of 15.9 centimeters. And then using a compass or something like that, that would give us a distance for the circumference of 1 meter. And then all you'd have to do is put a little mark on it and then just count how many times that mark pops up. So you could put a reference point somewhere on there or on the ground, and then just count how many times that reference point touches the ground: 1 meter, another meter, etc. And that's basically what the measuring wheel is doing, except it's using a reduction gear in order to spin this this dial that's counting, kind of like a odometer in a car, which is also pretty cool. Yay, mechanical devices. All right, so the evolution of the bicycle, mechanical devices. So the first bicycle, which again, just bicycle, so just 2 wheels is what it's referring to, was a Dreisine. So Dreisine came about in France in 1817, and essentially it was it didn't have any pedals or any gears or anything like that. You just kind of push yourself along. So it was kind of like sledding, I guess. Anyway, so really rudimentary. I don't know if you even really had steering or if you just leaned to steer. I'm not sure. I assume that the wheel would turn for steering, but anyway, kind of like a children's toy almost. Then we had the tricycle velocipede, a little ambitious with the word velocipede. But anyway, they attached levers to the back wheel and to the pedals, and kind of like how a locomotive works. You would just step up and down, and that would push the levers forward and back, causing it to move forward. And then the high wheel, which of course is very famous for high class society, yes. Then the safety bicycle, which came around because it was called the safety bicycle because the high wheel was not very safe, and so it was kind of a reaction to the market reaction to what was going on. And then more traditional racing street bikes, and then mountain bikes, which came around apparently in the 2000s. So the tricycle velocipede, you'll notice the radius of the two wheels are a little bit different, and if you notice, the pedals are attached to these rods here, and very similar to the rods that are attached to the wheels of a train or a locomotive. Now we use electric we use electric motors. That way they can go forward and backwards without having to reset. But anyway, or diesel powering electric, I think is how they do it now, but it doesn't matter. So these rods, they would basically just step up and down, kind of like going up and down stairs, and that would cause the bike to move forward. Well, they learned that the larger the wheel, the longer the circumference, and so the longer distance you travel for every revolution. So in an effort to make the bikes faster, they made the wheels as large as they can. And so the bikes, the high wheels, were actually customly made to fit the inseam of the operator. So, which is pretty interesting, so that his leg would be fully extended or almost fully extended at the bottom stroke of the bicycle. And so they actually fit pedals, and seat heights is how we adjust it now in bicycles for the most comfort and optimal range for where your legs are at, which is actually kind of cool. So, if we had 24, say that was 2 feet long, so kind of like the inseam or whatever, but be a little bit shorter than the inseam, I guess. But if that was 24 inches, then 24 times 2 pi would give us 48 pi, and so we can find that in inches by multiplying 48 times pi, converting it to a decimal, which would be 150 inches. And if we wanted to change that to feet, we could just divide it by 12. Looks like I did that back, but anyway, divided by 12, which would give us about 12.5 feet. So for every, which is ridiculous, right? So for every rotation of the pedals, the bike would travel 12.5 feet. So you bet he wasn't spinning the wheels very high with a very, very fast cadence. But anyway, the problem was the high wheel was very, very dangerous, and a lot of people were actually dying from wrecking their bicycles. And so it was kind of like a, I don't know, it's kind of, I don't know, he was showing off for the ladies. How about that? All right. Next thing we want to look at is arc length. So if we want to know what is not the circumference, the distance all the way around the circle, but the physical length of this arc. Now remember, the arc is the set of all points between two endpoints that are all equidistant from a center point. In other words, it's like a segment that's on a circle with two endpoints. So we want to know what's the physical length of this. Well, the best way and the most logical way to find the arc length is to find the fraction of the whole circle and then multiply it by your circumference. So in this case, the only clue that we have, the measurement of the circle is 90 degrees, right? We measure the circle in degrees by the central angle. But if I want to know the physical length of the arc, that's going to have to relate into the circumference and the radius of the circle. So to find the circumference, we do 2 times pi times r. Radius was 6 in this case, so it's 12 pi. So our arc length formula is going to be some fraction of the full 12 pi. So we don't want the whole red 12 pi here. We just want the blue arc, right? The measurement of the blue arc. So what fraction would I use? Well, our clue is going to come from the central angle. In this case, it's 90 degrees. And we know this would be a quarter of a circle, right? So it's a quarter section. So 90 divided by 180, or if we simplified it, just 1/4. So what's 1/4 of 12 pi? So if the whole thing is 12 pi, this part would be a fourth of that, which is just simply going to be, is equal to 3 pi. All right, so that gets us to our general formula. So the general formula that we have is whatever this degrees are in x for our central angle, we just divide that divided by the whole thing, which is 360. So in this case, that would have been 90 out of 360, which we reduce to 1/4. So this is our formula for the length of an arc. And it should make sense. Just logically, the 2 pi r is going to be the length of the whole thing. And then we multiply it by the fraction, which is how many degrees is our central angle out of the whole 360 degrees and the circle of oughtness. Lots of accents today. All right, so next one, we'll do another example. So the first thing we want to do is find the circumference of the whole thing with a radius of 3. So 3 times 2 would give us 6 pi. And so now we want to know what is the fraction of that. Well, we're interested in the 120 degrees, which is our central angle. So it's 120 out of 360 multiplied by 6 pi, which is the whole thing. So this reduces to 1/3, but you can also just put it in your calculator because some of them are not going to reduce quite as easily. So you can put it in as the n over d, the fraction button, if you like. That way you don't make any mistakes, but like we almost did earlier. But that divided by 360, and that's going to give us our fraction, which is 1/3, of course. Then we multiply that times 6 pi, and that will give us our answer of 2 pi. So if we leave this in exact form, yeah, it's totally 2 pi. I don't know what I was thinking. All right, so the length here is 2 pi. So what's the part that's left over? Well, if the whole thing was 6 pi and this is 2 pi, that means the leftover part over here in red would be 4 pi. All right, so that's it. New material only took about 13 minutes, so not too bad. If you'll get out your assignment, we'll go ahead and go through that together. So on number 1, we just want to find the circumference. So we're given the radius of 9, so plug it into our formula. 2 times 9 would give us 18 pi. Really simple. Now on 4 through the last part of the front page, we're going to find the arc length. So this is where we have to deal with the fraction of the full circumference. So it's really just like we just did to find the circumference, but now all we're doing is multiplying it by some fraction, which is the degrees out of 360 degrees of oughtness. So first part is our radius here is 20. So 20 times 2 is 40. So this is going to be 40 pi. And then our fraction, you're going to look for the bold part. So you'll notice this line is thinner on the assignment and this part is thicker. So we're looking for the thicker part. Yes, thick with 3 C's. Yeah, I'm just having all kinds of fun today. Anyway, so if this is 45 degrees, what's the part of the circle that we're interested in? So we just want to do 360 minus 45, which you might be able to do in your head, no big deal. Didn't quite catch that. There we go. 315. So our fraction is 315 out of 360 times the circumference of the whole thing, which was 40 pi. And when we put that in our calculator, it'll give us our answer. Struggling over here. So fraction button, 315 over 360. And then we're going to multiply that by 40 pi. You could leave the pi part off because it's just going to put it at the end anyway, but you can put it in if you want. So that's 35 pi, which will be our final answer. So this part, the blue part's 35 pi. So this part here it's going to be the 5 pi that's left over. And altogether, the whole thing will give us the circumference of 40 pi. All right, number 7. So this one can be a little challenging because the 18 feet, we don't know if it refers to the diameter or to the radius. Well, because it's closest to the full line, which would be the diameter, that's going to be the diameter. So to find our radius, it would just be half of that. But why would we half it if we're just going to double it again to find the circumference? So you can use either one of the formulas, either 2 pi times radius or pi times diameter. So if it's 9 for the radius, 2 times 9 would be 18. So in other words, it's just 18 pi. All right, so our fraction that we're looking for is going to be this part for the thicker line on the bottom. So if this is a semicircle and this is 30, that would mean that this part here has to be 150 degrees. So it'll be 150 out of 360 times our 18 pi, which is pi times the diameter. And we just plug that in our calculator and we'll see what we get. So we got 150 over 360. And then we multiply that by the whole thing, which was circumference of 18 pi. All right, so we get 15 over 2 pi. Now we can reduce that to a decimal. Now I did the whole decimal approximation. Okay, I don't like this. So instead, what I'm going to do is I'm just going to remove the pi part here, the pi portion, just to figure out what fraction of pi that is. So 15 divided by 2, you probably know, but it's 7.5. And that's how I wrote your answer in the answer bank. So I used decimals, but then I kept the pi part separate. So if you just want to put it in the calculator and leave the pi off until the very end and then just tack it on there, that's totally fine. So this should give you 7.5 pi. All right, number 12. So on this one, we have the diameter. So that means that the circumference is just pi times d, or 22 pi. We're looking for the semicircle, which is half of that. So what's half of 22 pi? 11 pi, right? Well, formally, if we did the whole formula, which I don't expect you to write down because you can do this one in your head, it's an easy fraction. So it's 180 degrees out of the 360 degree circle of altness multiplied by 22 pi, which leaves us with 11 pi. All right, 13. So on this one, we're looking for this part over here. That's the thicker line. The 15, because this is actually connected to an entire diameter here, we're going to say that that's not referring to the radius. If it was a part that didn't have the whole end, the whole diameter, then we would say that it was the radius. So for instance, if they put the number next to this right here, that would be referring to the radius. But if it's next to the entire diameter, then it refers to the diameter. So this is 15 is the diameter, so the circumference is 15 pi. Now, if this is both diameters, then the central angles are both 60. So that means the measurement of this arc is also 60. So you can move the 60 across all the way over there because they're all exactly the same. Because you measure central angles, the arcs by their central angles. So all those are 60 in other words. So our formula is 60 over 360, which is 1/6 of 15 pi. Okay, which is going to give us 2.5 pi. All right, 15. So we're on the back side. What angle is swept on an analog clock in 9 minutes? So if we started out at 3 o'clock, then goes all the way to 3:09, what angle was swept out in that amount of time? Let me change color real quick. There we go. So going to 3:09, that's nice. What angle is swept out in that amount of time? All right, so our fraction, our formula for figuring this one out, just kind of logically thinking through it, is exactly the same as with arc length. So we've got two parts of the formula. The first part's the fraction. So 9 minutes out of the whole, which is 60 minutes, right? So our fraction is 9 out of 60. Then we multiply that by the whole. Well, we want to know what angle, so the units we wanted it to be in is in degrees. So out of a full 360 degrees, excuse me, how many degrees was swept out in 9 minutes? So 9 out of 60 multiplied by 360. And we'll just put that in our calculator. So I'm going to do the fraction button again. I really like that fraction button. So 9 out of 60, and then we're going to multiply that by 360, which leaves us with 54. So 54 degrees were swept out. So this angle here would be 54 in 9 minutes. So you can do part B and part C by yourself. The answer bank's there. All right, so 18, we're going to go through the entire problem 18 together because it's pretty cool. I got some nice graphics for you as well. So 18 part A. Actually, let me pull up the assignment so I can follow along, read exactly what you guys are reading. Nice to have dual monitors.